All right, we're continuing with law of cosines. We're doing some application problems, which it really is my favorite part of law of cosines because we can actually do stuff. I find trig interesting when we can actually do stuff with it. So a motorized sailboat leaves Naples, Florida, bound for Key West, 150 miles away, maintaining a constant speed of 15 miles an hour, but encountering heavy crosswinds and strong currents. The crew finds after 4 hours the sailboat is off course by 20 degrees. We want to find how far the sailboat is from Key West at this time. We want to figure out through what angle should the sailboat turn to correct its course. And then lastly, we want to figure out how much time has been added. Well, we want to start with a good diagram. Good diagrams are always important for us. So it just so happens that Key West is almost due south of Naples, not exactly, but almost. And it says that Key West is 150 miles away. But they ended up getting blown off course by 20 degrees. So instead of traveling on this blue line, they ended up traveling. You guys mind muting your mics? Thank you. So we're off 20 degrees there. It said they went 15 miles an hour for 4 hours. So this distance, rate times time, is going to be 60 miles. Let's see, make sure that looks good. Okay. Questions at all on the diagram? Well, the first thing they want us to find is how long is this distance right here? There is nothing that tells us that this is a right triangle. Just because my picture looks kind of like a right triangle, we have no facts to back up that that is a right triangle, so we cannot use SOHCAHTOA or Pythagorean theorem or anything like that. I noticed that I do not have a known pair, so that rules out law of sines. I have, and I know one of the sides is a variable, but we're dealing with 3 sides and 1 angle. 3 sides and 1 angle is always law of cosines. We start with the side opposite the angle that we're talking about. For part A, we're going to get x squared equals 150 squared plus 60 squared minus 2 times 150 times 60 times sine of 20 degrees. Personally, I would just plug this whole thing in my calculator at once. I know x is going to be the square root of all of this, so I would just plug it all in at one time. And then we'll round to our nearest hundredth. I do not have this example in my notes worked out, so I will need an answer, please. Anybody get an answer?
I got 141.2.
Anybody else get that? That seems like a large number to me. Anybody else with an answer? You can put it in the chat if you don't want to talk. Oh, you got the same thing, 141.2. Huh, okay. All right, we're going to hundredths. That's 2.2. Okay, so that's how far they are away from Key West right then. In part B, we want to figure out through what angle should the sailboat turn to correct its course. Let's take a look at our diagram. If it keeps going on the path it is, it's going to keep going this way. So to turn, we need to figure out this angle right here. Well, that angle is not inside of our triangle. So what we want to do is we want to find this angle that is inside of our triangle, and then the angle that we need to turn is going to be the supplement to that. Because if I extending that red line, I have a straight line. So we'll start with finding that inside, and then the supplement will be our turn angle. Establish this is 141.22. Again, 3 sides and an angle. I'm going to use law of cosines. We could use law of sines, but then we have to watch out for the ambiguous case and all that. So I would be inclined to use law of cosines instead. We always want to start with the side across from the angle we're dealing with. 150 squared equals 60 squared plus 141.22 squared minus 2 times 60 times 141.22. Oh my gosh, I know why my answer in part A is wrong. What did I do, guys? Do you see it? Jeez. This is the law of cosines. Look, and I put sine in there. Jeez, oh man. All right, sorry, we got to do that again. Plugging in cosine.
I got 95.8.
That sounds way better to me. 95 point, I'm sorry, what?
95.841.
All right, so to the nearest hundredth, 8.4. Sorry about that, guys. Law of cosines, use cosine. Jeez, oh man. Everything I said about finding the next angle is true. It's just this side is 95.84 now. And then cosine, I guess I'll call this angle something. I'll call it theta. There we go. This one will take a little bit more cleanup. But again, I probably would just rearrange things and not get decimals and just plug it all in my calculator at once. These two things need to be subtracted over. And then I'll divide by these over here. If we do that, we'll end up with cosine of theta equal to 150 squared minus 60 squared minus 95.84 squared divided by -2 times 60 times 95.84. And then to find our angle theta, we're going to do inverse cosine of that fraction. And I would. So when we plug that in our calculator, round it to the nearest hundredth, well, what do we get? Make sure when you're plugging this into your calculator that you have parentheses around all this stuff in the numerator and parentheses around all the stuff in the denominator. What are our answers? Can't be just Alex, or we're never going to get through our material, and then it's going to be rush, rush at the end. I get theta, since I haven't plugged in my calculator, to be at 147.64 degrees.
I can confirm that.
Thank you. Here, I'm even pulling up a second computer so that I can see the chat, and I'm gonna just bring up the chat box so people can feel free to just answer via chat. Sorry, but I gotta figure out how to stop that. All right, so I have the chat box just open. For people to answer in. But that is not our answer. All right, now I'm trying to figure out how to not hear anything. Okay, so that's our angle theta on the inside of our triangle, but that's not our turn angle, right? Our turn angle is going to be the supplement of that. So our turn angle is actually going to be 32.36 degrees. Questions at all? Last thing we want to do is, will one turn, what? Will one turn always be 180 degrees? The reason that it's 180 degrees that we're subtracting from, Amber, is because our normal path would have been here, right? Which is a straight line, and straight angles are 180 degrees. So because we're going off of a straight line, if that's the case, then yes, we're always subtracting from 180 because that's our straight line. If we know how much this one is, then the one on the outside just has to be the supplement. All right, the last question. Right, it's the reference line. Right, it's the reference line, not yes to everything you have in the chat. The last thing it wants us to know is how much time has been added to the trip because of being blown off course. We want to assume that the speed remains at 15 miles per hour. So how would we figure out how much more time has been added to the trip? Well, we were originally traveling 150 miles at 15 miles an hour, so it would end up taking us 10 hours, but now we're going to be traveling 154.84 miles. So now we're traveling that much more, which is 5.84 miles more than planned. If we're going 15 miles per hour, how long is it going to take us to go that 5.84 extra miles? We know that distance is equal to rate times time. The extra distance is 5.84. Our rate is 15. We can find our time simply by dividing. Because our rate is in miles per hour, when we get this time number, it's going to be in terms of hours. So I'm getting 0.39 hours, but nobody really talks like that. So personally, I would multiply it by 60 to get minutes. It's going to take 23.36 extra minutes. If it doesn't specify which unit of time to use, I'll be happy to take either. Questions? We will certainly be seeing some application problems on our exam. There'll be some that are just straight, here are the numbers, solve the triangle, but we learned law of sines and law of cosines really to do applications. So we'll definitely be seeing several applications on this next exam. All right, let's try a couple more. The height of a radio tower is 500 feet, and the ground on one side of the tower slopes upward at an angle of 10 degrees. So I already have our diagram drawn for us. How long should a guy wire be if it's to connect to the top of the tower and be secured at a point on the slope side 100 feet from the base of the tower? We'll round our answer to the nearest hundredth. So again, I already have our diagram for us. So we're looking at this triangle here. We know that this side is 500, and we're trying to figure out our side X. Well, for any of these, we need three things to be known. And right now, looking at that green triangle, the only thing I know is a side of 500 and a side of 100. My side of X is what I'm going to find. So that means I have to know an angle measure to be able to get started. Is there any way to know an angle measure here? Yeah, it's going to be 80 degrees there because this bottom one is a right angle, and we know that that incline is 10 degrees. So when I do 90 minus 10 degrees, that makes this 80 degrees. I'm just going to draw a breakout triangle here for part A. Trying to find side X, knowing this side is 500, this is 80 degrees, and our bottom side is 100. I don't have a known pair, but I'm relating three sides in one angle, so that's definitely law of cosines. We always start with the side that's opposite of our angle. So this is going to be x squared equals 500 squared plus 100 squared minus 2 times 500 times 100 times cosine of 80 degrees. And just like our previous example, I would just plug all this in my calculator at once. I know that x is going to be the square root of all this. So we want to plug in and round to the nearest hundredth. I would encourage you, throughout class that you are practicing on your calculator. You don't want to find that you're having a calculator issue on test day. So I'd encourage you, I know it's boring to type it all in, but just for the practice. We should get a 492.58, and our unit is feet. Questions, anybody? Part B asks, how long should a second guy wire be if it's to be connected to the middle of the tower and secured at a point 100 feet from the base of the flat side? So now we're looking at this over here. The side is flat, so that means that we have a right angle right here. If this wire is only going halfway up this 500-foot tower, it means that this side here is 250. So for part B, I have this breakout triangle here. And I'm trying to find my side X. Do I need to use the law of cosines?
Wouldn't Pythagoras' theorem work because it's a right triangle?
Exactly. I mean, we could do law of cosines. It'll always work, but I would just do Pythagorean theorem here because I'm relating the three sides of a right triangle. So our hypotenuse squared is the sum of each of our sides squared. So x is going to be the square root of 100 squared plus 250 squared. I always try to find the easiest approach. We know a lot of math. Oh, I shouldn't use x. I'm going to use a different variable, not to be confused with the x in part A. Rounding to the nearest hundredth, we should get 269.26, and our unit again is feet. Questions, anybody? All right, our last one. A surveyor wishes to find the distance between two inaccessible points A and B on opposite sides of a lake. While standing at point C, she finds that B equals 259 meters, while A equals 423 meters. The angle ABC, or no, I'm sorry, ACB, so this angle here, measures 132 degrees, 40 minutes. We want to find our distance C. We'll round our answer to the nearest hundredth. All right, I'm gonna pause the video, put you guys in groups, and let you guys work this one out. Since we already have the diagram for us, that's the tough part. So we'll use Heron's formula for side, side, side. Let me scroll back up just so people can see the answer to this one, since I forgot to start the recording back up. All right, for Heron's formula, the first thing we need to do is find what's called the semi-perimeter. And I don't know why, when I was a student, I just didn't wrap my brain around what that meant. Semi means half. You know what the perimeter is, add up all the sides. So our semi-perimeter is S equals 1/2 A plus B plus C. So it's just the perimeter divided by 2. Then the area of the triangle is going to be A equals the square root of S times S minus A times S minus B times S minus C. So basically the area is the square root of the semi-perimeter times the difference between the semi-perimeter and each of the 3 sides. So the dimensions of a triangular lot are 100 feet by 50 feet by 75 feet. If the price of such land is $3 per square foot, we want to figure out how much the triangular lot costs. We'll start by finding our semi-perimeter, which is just add up all the sides and divide by 2. It's going to be 112.5. Then the area of the triangle is going to be the square root of 112.5 times the difference between that 112.5 and each of the sides. And then we want to plug all that into our calculator. The area ends up being 1,815.46 square feet. But the question is, how much does the lot cost if it's $3 per square foot? So we'll have to take, for the cost, $3 times our area, and we'll round to the nearest cent, 5,446.38. Questions at all? All right, why don't you guys try the next one? I'm not even going to put you in groups unless you want me to. Do you want me to put you in groups to do this next one? So I ended up getting 401,664.11 square miles. Anybody get anything different? All right, Heron's formula. I would definitely, as I'm preparing for this next exam in one-on-one conversations during office hours and stuff, I've talked with some of you about preparing differently for an open book test. I would definitely have a category that said area of a triangle and put our 3 formulas down and write down when we use which one. Because of course, I'm not going to say on the test, oh, use Heron's formula or use sine to find this area. We're going to need to know that Heron's formula is for 3 sides. And sine, when we use that sine one, is when we have 2 sides in the included angle. All right, so now we're moving on to vectors. It's an application of all this trig stuff. So I got a lot of talking to do here in the beginning, a lot of setup. So if you have any questions about all this, please be sure to stop me. A quantity that involves magnitude is called a scalar quantity. These quantities are represented by real numbers. That's why the word scalar number, just means real number. A quantity that involves both magnitude and direction is called a vector quantity. So they tell you how big it is and how it's pointing. That's a vector quantity. The magnitude of a vector quantity represents the length of the vector. The direction of the vector, indicated by the arrowhead, represents the direction of the vector quantity. Typical vector quantities are velocity, acceleration, and force. So, for example, the velocity of an aircraft can be represented by an arrow that points in the direction of movement. The length of the arrow represents the speed. Thus, if the aircraft speeds up, we lengthen the arrow. If the aircraft changes direction, we introduce a new arrow in that new direction. So you'll notice over here, we got these 2 vectors. The larger speed has a longer vector. And then over here, this is where we change direction. So if we're changing direction, we introduce a new vector altogether. They're always straight lines. You're not going to draw a vector and then curve it. Straight lines put together. The symbol for a vector is often printed in boldface type, but we don't usually write boldface when we're writing by hand. So when we're writing by hand, it's customary to use an arrow over the letter or letters. So I know that's small there, but we see we have an arrow pointing over our letter V. Vectors can be named with either 1 lowercase or uppercase letter or 2 uppercase letters. When 2 letters are used, the first letter indicates the initial point and the second letter indicates the terminal point of the vector. Knowing these points gives the direction of the vector. So for example, vectors OP and PO are not the same vector. They have the same magnitude but are going in opposite direction. So this first one here, this is OP because we're starting at O and then extending towards P. And then the second one is our PO because we're starting at P and extending towards O. The magnitude of a vector, and vector OP specifically here, is written where it has like absolute value brackets around it. It is a fact that 2 vectors are equal if and only if both their direction and magnitude are the same. Equal vectors need not coincide, but they have to be parallel to each other. Equal vectors, same direction, same magnitude. So let's talk about adding vectors. Suppose that 2 horses are pulling on a tree stump with forces of 200 pounds and 300 pounds with an angle of 65 degrees between the 2 forces. The 2 forces are represented by vectors A and B. If vectors A and B had the exact same directions, then there would be a total force of 500 pounds acting on the stump. We just add up the 2 vectors. But since there is an angle of 65 degrees between the 2 forces, that total force of 500 pounds is not achieved. See, the two horses are kind of fighting each other a little bit because they're not pulling in exactly the same direction. A little bit of it is counterproductive because they're pulling against each other. It turns out that one force acting along the diagonal of the parallelogram created by these two vectors with a magnitude equal to the length of the diagonal has the same effect on the stump as the two forces A and B do. This idea is called parallelogram rule. So we started with just these two vectors A and B. If we want to figure out what the force is when you add those two together, we're going to create a parallelogram. Recall that a parallelogram is a quadrilateral with two pairs of equal parallel sides. So it's just like a rectangle that's kind of been pushed over. So what happens is we create a parallelogram, and then the diagonal of the parallelogram is what represents the vector A plus the vector B. We're going to use parallelogram rule a lot in application problems. The single force A plus B acting along this diagonal is the sum of the two vectors, or we call it the resultant vector. Please note that the sum of two vectors is also a vector. So here I'm illustrating parallelogram rule away from the diagram, kind of done a breakout picture here. For parallelogram rule, we want to position the vectors A and B so their initial sides, or their initial points, coincide. Then we're going to complete a parallelogram that has A and B as its two sides. The diagonal of the parallelogram with the same initial point as A and B is the sum A plus B. There is another way to find the sum of two vectors. What we can do this time is position the vectors A and B so that the terminal point of A coincides with the initial point of B. The vector A plus B is then the unique vector that connects the initial point of A with the terminal point of B. So with parallelogram rule, the two initial points are the same. It's like I always think of the horses. It's going to be two forces acting on the same point. But the other way to add, you're kind of you draw one vector, and then where that first vector ends, you then start the next vector, and then the sum of those two vectors is just, I don't want to say the diagonal or the hypotenuse because it's not a right triangle, but the side that connects the two. So you may be thinking, well, how do I know when to use which rule? You'll know by the context of the application. We're going to use parallelogram rule anytime we have two forces acting on a single point. If we're using this technique, then it'll tell you that the diagram where that one vector starts where the other one stops. Maybe an airplane's changing direction. So you're only going to have one object or one force typically. All right, so we've got some properties of vectors. First off, vector addition is commutative and associative. So we can flip-flop the order, or we can group the addition however we like. We're going to find as we go through this section on vectors that vectors have a lot of the same properties as real numbers, which I think makes sense because we said in the very beginning when we defined a vector, right? A quantity that involves magnitude is a scalar quantity, and these are represented by real numbers, and vectors have magnitude to it. So these vectors tend to follow the same rules as our real numbers. So addition is both commutative and associative. The vector A, whose magnitude is 0, is called the zero vector, and it is assigned no direction. It is a fact, if you take a vector and add the 0 vector to it, you get that original vector back. That's the same as our additive identity in real numbers. Any number plus 0, is that 0? I'm sorry, I've been talking a long time. Anybody got any questions so far? All right, for every vector A, there is a vector negative A that has the same magnitude as A, but opposite direction. This vector is called the opposite of vector A. Again, same as real numbers. 2 and -2 are opposites of each other. It is a fact that if you take a vector and add the opposite vector to it, you get the 0 vector. Again, we see that in addition of real numbers. 2 plus -2 equals 0. Same thing happening. If A and B are vectors, we define the difference, A minus B, as adding the opposite, A plus -B, just like we did when we first learned adding and subtracting integers. The scalar product of a real number, or scalar k, because sometimes we don't say real number, we'll just call it a scalar number. So the scalar product of a real number k and a vector u is the vector k times u, which has a magnitude of the absolute value of k times the magnitude of u. So that scalar just makes our vector get longer. How much longer? Well, k times longer. Magnitude, though, we always talk about in terms of a positive number, so that's why it said that the magnitude is the absolute value of k times longer than the magnitude of u. If that scalar k is positive, greater than 0, then the vector ku will have the same direction as u, but if that scalar we multiply by is negative, less than 0, then the vector ku has the opposite direction as u. So we've got some properties of scalar products, and these properties we'll see are really the same as our properties of multiplying real numbers. 0 times any vector is the 0 vector. 1 times any vector is that vector. -1 times any vector is the opposite vector. Properties 4 and 5 here just have to do with distribution. It's just saying that if you have a sum times a vector, you can just distribute the vector in, or if you're supposed to add two vectors and multiply by a scalar, you can just distribute it in. Honestly, I don't typically distribute. I usually clean up what's inside the parentheses first and then just multiply one time, but we can distribute if we so choose to. And then number 6 is just the associative property, where we can rearrange the order in which we multiply things together. So if you have a scalar times a vector, you can multiply the two scalars together first and then multiply it by the vector. So again, vectors are following the same properties of addition and multiplication for real numbers. Any questions so far? Well, let's take a look at vectors in the rectangular coordinate system then. A vector v for which the magnitude of v is equal to 1 is called the unit vector. We use the word unit a lot in math to represent something of size 1, like the unit circle is our circle with a radius of 1. Two very useful unit vectors are I and j. I is equal to the vector 1, 0, and j is equal to the vector 0, 1. See how those, they look kind of like ordered pairs, but not quite because they're not parentheses. Those are called angle brackets. Anytime we see those pointy parentheses, those angle brackets, we know we're talking about vectors. So vector I is the unit vector whose direction is along the positive x-axis, 1 unit. That's why we call it 1, 0, because it's ending at the point 1, 0. And vector j is the unit vector whose direction is along the positive y-axis. So it's going 1 unit up the positive y-axis. We call it 0, 1 because it's ending at the point 0, 1. With the unit vectors I and j, we can express any other vector, AB, in the form AI plus BJ. So our vector V, which is defined 3, 4, that can be rewritten as 3I plus 4j. Vector 3, 4 should be ending at the point 3, 4. So here's our vector V here, and it's ending at the point 3, 4. But if we kind of make a triangle out of that, right, we see we're 3 across the bottom and then 4 up the side. And I is defined to be the unit vector of length just 1 going across the x-axis. So if I need it to be 3, that's going to be 3 times 1. And our unit vector j is going up 1 unit. Well, if I need to go up 4 units, I'm calling it 4j. So any vector v equal to ab can be rewritten as the vector v equals ai plus bj. I usually use this notation. It's less to write. Questions so far? A vector with this initial point at the origin is called a position vector. A position vector v with its endpoints at AB is written with those angle brackets AB. So our vector v is equal to AB. This means that every vector in the real plane corresponds to an ordered pair of real numbers. Thus, geometrically, a vector is a directed line segment, but algebraically, it's an ordered pair. The numbers a and b are the horizontal and vertical components of our vector v. So a is our horizontal component, b is our vertical component. We can represent vectors in rectangular coordinates. The vector v with initial point of p1 equal to x1, y1, and terminal point p2 equal to x2, y2 is equal to the position vector v equals x2 minus x1i plus y2 minus y1j. Here, let me draw you a picture about this. Well, we know that a position vector starts at the origin, but this didn't say anything about our vector being a position vector. So say my vector starts here and ends here. To write this in my AI plus BJ form, I need to figure out how far across and how far up we're going from our initial point to our terminal point. So this is the point 2, 1. This is 6, 5. So it's kind of like how we find slope, right? Rise over run. So my run, I'm going from 2 to 6. So this is 4. And then I'm going from 1 to 5. Oh, that's also 4. We could have just counted over, or we can subtract 6 minus 2 to get 4, 5 minus 1 to get 4, and then we get 4i plus 4j. And that's all they're saying right here. All right, we subtracted the x values to get the coefficient of I, and then we subtracted the y values to get the coefficient of j, just like we do with slope. Questions at all on that? Let's talk about the algebraic interpretation of vectors. Let's consider the position vector on the Cartesian plane. So position vector means the initial points at the origin. The positive angle between the x-axis and a position vector is called the direction angle for our vector. So here's our position vector here, and the angle that's made between the x-axis and that position vector is our direction angle. Let's talk about how we find the magnitude and direction angle of a position vector. Well, the magnitude is just the length of that. So look at this. We've created ourselves a right triangle. If I want to find the length of vector u, which is essentially the hypotenuse of this right triangle, I'm just going to do Pythagorean theorem. A squared plus b squared equals u squared. So if I want to just solve for u, we get that u is equal to the square root of a squared plus b squared, and that's our formula for magnitude of a vector. It's just an application of the Pythagorean theorem. To find the direction angle, well, take a look at this. We've got this right triangle, so not only does Pythagorean theorem apply, but SOHCAHTOA applies. My sides, A and B, because that's the information we're given when we have this vector u, they give us the A and the B. If I'm looking at my angle theta compared to A and B, SOHCAHTOA applies, and I get that tangent of theta is equal to B over A. This is the fact that we're going to be using to find our direction angle. Any questions? Well, let's talk about properties of the magnitude of u. Now, the magnitude is the length. So just like any length that we talk about, we don't talk about the side of a table being a negative number. So the magnitude of some vector can't be negative. It has to be greater than or equal to 0. The only time the magnitude of a vector is actually equal to 0 is when that vector itself is the 0 vector. The magnitude of a vector and its opposite vector are the same. I mean, we got that in the definition of opposite vector. Same magnitude, opposite direction. So the magnitude of a vector and its opposite vector are the same. And then lastly, number 4, the magnitude of some vector times a scalar k is equal to the absolute value of that scalar times the magnitude of u. So here, these properties of magnitude follow all the rules for absolute value. Everything here applies to absolute value as well, which is why I love that they use the same notation for magnitude of a vector and absolute value, because it follows all the same property. If you took 103 with me when we did, I think, even and odd functions, I talked in depth about some properties of absolute value, and it included this property number 4 listed for magnitude of a vector. All right, so let's practice finding the magnitude and direction angles for a vector u. Here, u is equal to -724. And again, I know this is a vector because we have angle brackets. To find the magnitude, this is equal to the square root of a squared plus b squared. It's just Pythagorean theorem. That's going to be -7 squared plus 24 squared. Which is equal to, what's that, the square root of 525. Which equals 25. Everybody good with 25? Any questions? To find our direction angle, we're using the fact that tangent of theta equals b over a. Oh, tangent of theta equals 24 over -7, which means theta is going to be tan inverse of 24 over -7. Well, I'd love it if somebody could plug this in their calculator, because we're going to get something that we need to work with here at the end. So if somebody could give me this actual value in their calculator.
Should I give it?
Oh, James already beat you to it.
Oh.
In the chat. I think I'm just going to go to hundredths here. All right, so we get -73.74. Because remember, our calculator, when it does inverse tangent, does it by definition, and it only spits us out an answer from -90 to 90. But what we need to do is think about where this vector is. And we can do that by simply looking at the location of the ordered pair, thinking of it as in terms of an ordered pair. So if we are at -724, that means that we're in quadrant 2 somewhere. But the angle that our calculator spit out is down here. Right? So our calculator gave us the wrong quadrant, because quadrant 2 is not in the range of inverse tangent. So how are we going to get from quadrant 4 over to quadrant 2? That's right, James. All we're going to do is add 180 degrees to get into quadrant 2. So our real direction angle equals 106.26 degrees. So when you find your direction angle, it's important that you also plot the actual vector so that you know if you need to add 180 or not. Question. All right, I think I'm going to run like 5 minutes over just so we're at a decent, like a stopping point that makes sense for the exam. So sorry. If you need to go, it'll be posted online for you to watch the rest of it. All right, let's do the same thing with this vector u. We want to find the magnitude and the direction. The magnitude of vector u is going to be the square root of 8 square root of 2 squared plus 8 square root of 2 squared. It's going to be the square root of 128 plus 128 square root of 256, which is a perfect 16. And then to find our direction angle, we're using tangent of theta equals b over a. So tangent of theta equals 8 square root of 2 over -8 square root of 2. It's going to simplify to be -1. So theta equals tan inverse of -1. We want to pop this in our calculator. Our calculator is going to give us negative 45 degrees. But just like in the last one, we kind of got to picture where this vector is to make sure that we're in the right quadrant. Oh, we have a positive x value and a negative y value. That means that our vector u is in quadrant number 3. Does our direction angle give us, put us in quadrant 3? It does, but if you go back to the definition of direction angle, the direction angle is the positive angle between the x-axis and the position vector. Right now, we have a negative angle, negative 45 degrees. So we just need to find the positive coterminal angle here by adding 360, and we get a direction angle of 315. Questions at all? Okay. All right, I just got these couple more examples here. Vector operations. If you want to add two vectors, all you do is add the first two components and then add the second two components. That's it. If you want to multiply a vector by a scalar, you just distribute that scalar in. Multiply the first component by the scalar, the second component by the scalar. If vector A equals A1, A2, then vector negative A equals negative 1, A negative. Sorry, negative A1 and negative A2. So to me, that's just the same as property number 2, because that's like having a negative 1 out in front, and I'm just going to distribute that negative 1 to each of my components. And then number 4, yeah, that's super similar to number 1. If we want to subtract two vectors, we're going to subtract the first two components and then the second two components. So here I've given you two vectors. In part A, we want to find u minus v. Please do not make this hard. All we're going to do is subtract the first two and then the second two. So it's going to be negative 2 minus 4 and then 5 minus 3, keeping it in angle brackets. We get the vector negative 6, 2. That's it. Questions at all? In part B, we want to find go ahead.
Mrs. Kraft, I had a quick question. How do we define the angle brackets in D2L?
I don't know. You mean in my math lab?
Yeah, in my math lab.
I imagine at the bottom, I don't know. I'm very confident though that at the bottom, you know how where they have like that tool palette and they give you all kinds of options. I bet there's gonna be one that looks like this.
Okay, thank you.
Yeah. If there's not, let me know, but I'm betting on that. For negative 5 times vector v, all we're doing is taking the negative 5 and distributing it into the two components in our vector v. This is going to give us negative 20, negative 15. That's it. In part C, I'm combining the idea of addition and multiplication. Order of operations continues to rule the math world, so we'll follow order of operations. Since we have multiplication, addition, and subtraction happening, we'll do the multiplication first. We're going to have 2 times vector u plus vector v minus 6 times vector v. Now, by the way, these are like vectors. You could combine that to be just minus 5v. I'm gonna do it the long way, but you could, if they're the same vector, combine them. All right, we're gonna multiply first. Negative 410 plus 4,3. Now here, I would totally distribute the negative, just like I would if they were polynomials, and turn this into plus. And then we're adding our 3 first components together, and then our 3 second components together. It's going to give us negative 24, negative 5. Questions? Almost done. Last thing will take me 2 minutes, and then this will be where we stop with material for the exam. Horizontal and vertical components. The horizontal and vertical components, respectively, of a vector v having magnitude of v and direction angle theta are given by A equals the magnitude of v times cosine of theta, and B equals the magnitude of v times sine of theta. So this just comes from SOHCAHTOA. Right, so we've got this vector v with sides A and B and our direction angle. We're just doing SOHCAHTOA, so I can say that sine of theta is equal to B, right, opposite over hypotenuse. And then I solve it for B. I get B equals the magnitude of V times sine of theta. So that's this one. And then for the other one, I'm just using cosine with SOHCAHTOA. So cosine of theta is equal to adjacent over hypotenuse. And then solving for A, I get A to be the magnitude of V times cosine of theta. So these really aren't new formulas. It's just applying a formula we already know in a slightly different way.
Mrs. Kraft, could you move the camera over? I'm having a hard time seeing to the right, so that way I can see the formulas you wrote out. Thank you.
There, is that better?
Yes, it is. Thank you. Could you hold there for just a second?
Sure.
All right, I'm good. Thank you.
Because we've now defined A and B in terms of the magnitude of our vector and sine and cosine, we can just kind of adjust our AI plus BJ notation. So this is AI plus BJ. That's all this is saying. All right, well, we're going to use these formulas here. A equals the magnitude of V times cosine of theta, and B equals the magnitude of V times sine of theta to find the horizontal and vertical components of a vector V given an angle of inclination alpha from our from the horizontal. So again, don't make this hard. They give us our angle, they give us our magnitude. All we're doing is plugging it into those two formulas for A and B. A is going to be 26 times cosine of 26, and then B, oh, no, times cosine of 50, sorry. And then B is going to be 26 times sine of 50, and I'm just going to pop those in my calculator. A equals 16.7. B equals 19.92. And then we could either write that with our angle brackets or in our AI plus BJ notation. So that'd be 16.71I plus 19.92J. And there we go. that will be the end of the material on our exam next week. Thank you very much for staying late. Sorry I ran 10 over, but I wanted to get to a good stopping point for our test next week. On Tuesday, I'll continue with vectors. We'll talk about dot product and applications of vectors. And then Thursday next week will be our exam. All right, well, everyone have, oh, I see, this is showing 2 videos. Look at that. All right, so everybody have a great weekend, and if you have any questions, please let me know. I am going to close out this meeting, so for any of you who are 103 who are popping in, I am going to close out this whole meeting so that this meeting can, like, this recording can process.
So Mrs. Kraft, we come